All right, some circuits questions. All right, we have a battery, EMF E, three identical incandescent light bulbs with a switch. The bulbs each have resistance R. Students make predictions about what will happen to the brightness of the bulbs after the switch is closed. So part A, a student makes the following prediction. Bulb 1 will decrease in brightness when the switch is closed. Okay, do we agree or disagree with the student's prediction about the bulb? Um, Derive an expression for the power expended by bulb 1 after the switch is closed, and how does your result uh, explain that? Okay, so first of all, let's think about this qualitatively, no numbers. All right, so we close the switch. All right, so before the switch is closed, we have sort of one path here going around. After the switch is closed, we're adding another lane for traffic here. Okay, when that happens, the resistance of this guy is going to decrease. That means the total resistance is going to decrease, so the current is going to increase, the overall current for the circuit. That means the current going through circuit number one, through light bulb number one, is going to increase. So will bulb one decrease in brightness? No, it's going to increase in brightness. Okay. Part two, before the switch is closed, the power is P1. Drive an expression for the power P new expended by the bulb one after. Okay. So P equals V times I. All right. So we really have to analyze this whole circuit here. Um, so we have EMF E, that's our total voltage. Okay. And before the switch is closed, this is let's make a before before the switch is closed, the resistance is just 2 times R, right? Okay. The voltage on the total, all right, the current is equal to voltage over 2R. Okay, that's the current for the circuit. And the voltage for V1 is going to be half of the total voltage, right? If this is 12 volts, then this will be 6, and this will be 6, right? Because they're equal resistance, it's going to split equally. So V1 will be equal to E over 2. All right, so P1 equals E squared over 4R. E squared over 4R, right? I'm just putting in this for V and this for I. Okay, that's our P1. Now for P2, um, we're changing things up a bit. So now the resistance of this guy is now R over 2. This guy is still R. So the total resistance is going to be 3 halves R. Okay, so the total current is going to be E, so I2, let me E over 3 halves R. All right, and the voltage is not going to be split up 50-50, right? So, right, because this is a bigger R than this one. This one's going to get twice as much voltage. So the voltage is going to be split 2/3 and 1/3. Okay, so V2 equals 2/3 of E. All right, so we combine those, we get P2 equals, so we have E squared, um, it's 4 E squared over R times 4/9. Let me check. Yeah, so P2 is 16 over 9, right? Because we have the 4 there and the 4 there. Um, 16 over 9 P1. All right, so P2 is going to be brighter, is more powerful than P1, and that's what we said in the first part, that the brightness would increase. So that's good. It's always good when things work out. All right, part B, a student makes the following prediction about bulb 2. Bulb 2 will decrease in brightness after the switch is closed. Okay, let me clear some ink here. Okay, do you agree or disagree with the student's prediction about bulb 2? And justify your explanation with a calculation. All right, so this one's a little more complicated. Okay, this one's a little more complicated. So remember, brightness relates to power, and P equals V times I. Okay, now I know the I for the whole circuits. So when I close the switch, when we close the switch, we know the R for the whole circuit decreases. Okay, that means the I for the whole circuit increases. But, and this is an important but, we have an increased I going through here, but then that gets split in half. Some of it goes this way and some of it goes that way. So overall, so the overall I increases, but the I2 decreases. All right. And since our resistance didn't go down by half, this I isn't doubled, which is we need to double that in order for I2 to stay the same. Um, so the I2 is going to decrease basically because we're splitting it between 2 and 3. Okay, before the switch is closed, all the current's going through I2. After the switch is closed, half goes through I2 and half goes through I3. All right. Also, remember what we talked about last time. Since this guy has value of R and these two have a value of R over 2, this guy is getting more than half of the voltage. It's getting 2/3 of the voltage, and this guy's getting 1/3 of the voltage. Why did I write P equals V over I? It's P equals V times I. Okay, so we're getting less voltage, right? Before we switched it, I2 and I1 had the same voltage. Um, Afterwards, the V is going to decrease, the I is going to decrease. This makes the brightness decrease, the power decreases. So the explanation is the current's getting split between 2 and 3, and the voltage is going to be less also, which causes a drop in power. All right, now we're adding a capacitor. We're replacing bulb 3 with a capacitor. So putting a capacitor here, right? That's a capacitor now. The switch is closed. How does the brightness of bulb 1 compare to the brightness of bulb 2 immediately after the switch is closed? All right, so immediately after the switch is closed, okay, this is just the capacitor just acts as a wire, okay? So none of the current's going to go through bulb number 2 right now. Bulb number 2 is going to be off. All the current's going to go through this. It's basically a free, um, why would you take this one lane road through here when we have a like 50 lane highway going this way? Okay, it's a short circuit. Bulb 2 isn't going to light up at all. Okay, so the brightness of bulb 1 will be brighter than the brightness of bulb 2. All right, after it's been closed, now for part 2, after it's been closed for a long time, all right, so now it's closed for a long time. Now no current goes this way. All the current's going to go through um, bulb number 2, okay? And bulb 1 and 2 have the same resistance. They're going to be the same brightness. It's the same current going through both of them. Remember, nothing's going up top. They have the same voltage because the voltage is going to be split 50-50 there and there. So the brightness of bulb 1 and 2 is going to be the same current, same voltage. All right, here's another one. Students are given resistor 1 with resistance R1 connected in series with the parallel combination of switch S and resistor 2 with resistance R2. The circuit elements cannot be disconnected from each other, and other circuit components can only be connected at points A and B. Students are given an ammeter and a 9-volt battery. The teacher instructs the students to take measurements that can be used to determine R1 and R2. So complete the diagram below to show how the ammeter and battery should be connected to experimentally determine the resistance of each resistor. Okay, so let's draw it right here. So we need our ammeter, okay, and our battery, okay. That's only half the battle though. So what you would do Okay, you would do this in two steps. So first, make a measurement, ammeter measurement, with the switch closed. Okay, so we start with closed. Okay, with the switch closed. When the switch is closed, we're shorting out R2. Okay, no current's going to go through R2. It's going to go through R1, then through just the short circuit there, and then back to the battery. Okay, um, so then we could do I equals V over R. Okay, we're going to know the I because we measure the I, right? So we're looking for R. So R equals V over I. So R1 equals 9 volts V over I1, whatever we measure that to. Okay, then you're going to do the experiment again, but this time we're going to do it open. Okay, now we're going to do the same thing. So we're going to have R equals, it's going to be V over I2. But this resistance is going to be R1 plus R2. When the switch is open, we just have R1 and R2 in series. It's going to go through the ammeter, through R1, through R2, and back to the battery. Nothing's going to go through the switch. So it's R1 plus R2 equals V over I2. All right? And since we know R1 from here, we can solve for R2. So R2 equals V over I2 minus R1. There we go. Okay. A second group of students is given a combination of circuit elements that's similar to the previous one, but has an initially uncharged capacitor. Um, the students close the switch and immediately begin to record the current through point B. The initial current is 0.9 amps, and after a long time, the current is 0.3 amps. Compare the currents through resistor 1, resistor 2, and the switch immediately after the switch is closed to the currents a long time after the switch is closed. Okay. Um, so, going to be connected to a battery, right? All right, so immediately after the switch is closed, again, it's a short circuit. Okay, immediately after the switch is closed, um, we're going to have no current through R2. All the current's going to be going through that way, right? Um, and again, we're going to be at the 0.9 amps. Okay, so R1 is going to be getting 0.9 amps, R2 is going to be getting 0. Okay, after it's been closed for a long time, now it's an open circuit. Okay, now R1 is going to be getting the 0.3 amps, right? And R2 is going to be getting 0.3 amps, right? And then it's going to go back through there. Okay, so again, immediately when the switch is closed, we get the total 0.9 amps going through R1. Nothing's going through R2 because we have a short circuit on the bottom. Now, after it's been on a long time, we lose our short circuit. So R2 is increased our resistance, which makes our current drop to 0.3. So R1 gets 0.3, nothing's going across the capacitor, R2 is also 0.3. All right, and calculate the values of R1 and R2. So again, R equals V over I. The V is 9 volts. Okay, so it's 9 volts over, so at the beginning, it's just R1, right? So R1 is 9 volts over 0.9 amps. So 9 over 0.9 is 10 ohms. All right, determine the value of R2. All right, so after it's been on a long time, okay, our total resistance is 9 volts over 0.3 amps. So that's going to be 30 ohms. And we know this guy's 10. So what does this guy have to be? It's 20 ohms, because that's to add up to 30. Determine the potential difference across the capacitor a long time after the switch is closed. All right, so after the switch has been closed a long time, right, the potential difference or voltage across the capacitor is going to be the same as the voltage across R2. Okay, because if I connected my voltmeter here and here, that's the same as the equivalent spots on R2, right? That capacitor is in parallel to R2, so they share that. So we just need to find the voltage on R2 after it's been closed a long time. So V equals IR. All right. The I is our zero point 0.3 amps after a long time, zero point 0.3 amps. The R is 20 ohms. So zero point 0.3 times 20 is 6 volts. 6 volts. All right, third group of students now uses the combination of circuit elements with the capacitor. I should have drawn that. They connect it to a 9-volt battery that they treat as ideal, but it's actually not ideal and has internal resistance. Okay, so how does the third group's value of R1 calculated from the data they collected compared to the second group's value? All right, let me draw that again. Okay, so we have a battery with an internal resistance. Okay, I should have drawn that the other way. This internal resistance R is going to behave just like R1. Okay, um, basically, when we measure, so this R is in series with R1. It's not on a separate path. We can just treat the resistance of these two as being the same. So when they measure R1, when they think they're measuring R1, they're measuring R1 plus R. Okay, so their value of R1 is going to be higher because they're measuring R1 plus the internal resistance. Um, yeah, basically they're measuring the value of R1 plus the internal resistance there. All right, the capacitor, the switch is going to have no effect on R1, and it's going to have no effect on the internal resistance. All right, any questions? Office hours or email me. Not going to go over any more stuff. If you have any questions, let me know. All right.